Here in the lab, they perform multiple biological sensing experiments, including ELISA tests and blood tests. ELISA stands for Enzyme-Linked Immunoabsorbance Assay and is a versatile test for pathology. The test requires a liquid sample from a patient and uses it to check for antigens via an antibody assay. The traditional method used to run ELISA assays uses expensive and cumbersome medical equipment. But the basic principle is that when antigens interact with antibodies, the color of the solution changes. The magnitude of this color change can be translated to a measure of the level of antibodies in the sample, which can then be used for medical diagnosis. Often, this test can be used to detect levels of progesterone, a sexual steroid that can be a sign of complications in early pregnancy among a wide variety of other things. Also, in the lab they do coagulation kinetics testing, which looks at the rate of how a blood sample coagulates. These tests are useful in preventative detection of patients with a high risk of stroke. The traditional testing method uses a thromboelastograph that measures changes in viscosity over time. In our technique, a technician places about 10 microliters of a sample in a capillary and measures the difference in volume as the sample coagulates over a period of time. The rate of change in this volume can be interpreted as the rate of coagulation. The lab has devised a 3D printed phone attachment for home use that can measure this change in volume after a period of time. But to do the test, it requires the sample be at a controlled, constant temperature, and they are also looking to expand the test into ELISA detection.
At the start of the semester, we were shown some enclosure designs with the idea of a cell phone attachment, and expanded on the ideas in order to automate the test, removing user error. We aimed to place a heated copper plate in a 3D printed box, with placeholders to secure ELISA testing cups. Instead of a cell phone camera taking the pictures, we purchased a camera for an Arduino microcontroller that would be mounted in the roof of the enclosure. The camera is manually operated, but with continued research efforts, there are possibilities for automated picture capabilities. In order to measure the levels of antigens in the samples, a backlight is required in order for the camera to pick up the changes in color of the samples. Here is one of the rough prototypes that we designed in the lab to test the automated heating function and the effectiveness of heating. This is a sample-sized box we designed in the early prototyping stages to verify the effectiveness of 3D printing for our uses.
Inside of the box is a copper plate in which holes are drilled into it in order to place ELISA cups. On the bottom of the copper plate, a heating element is attached that is controlled to 37 degrees Celsius by the microcontroller. On the copper plate, we can also store capillaries. On the top of the box, there is the camera that will take pictures for color analysis of the ELISA cups. On the right side, we have all the circuitry components that are required in order to run the microcontroller. And of course, a door.
While we made some important innovations, there are still many goals to reach before this device is ready for market. We hope to drastically reduce the current price to produce, which can be achieved through mass production as well as making improvements to the internal components. The goal is to ultimately deliver a product that improves the way families monitor their pregnancies, as well as providing labs with a cheaper alternative to current ELISA techniques. We aim to change the future.